Great, thank you. Yes, so my name is Koen van Dam. I'm with the Center for Process Systems Engineering, indeed the Chemical Engineering Department. So coming in from a different angle, my own background is in artificial intelligence and computer science and using computer tools to support our decision making. So that's what I want to talk about here today on decision support tools that will help with infrastructure investments, with infrastructure operation, and give feedback to the designers, to those who are operating this in a meaningful way. I have stressed here socio-technical infrastructure systems, and indeed, as David said, I will emphasize and I will argue today that we do need to include that social element in our decision support tools, and we need from our bridges, we need our sensors so that we know that they're going to fail. But if we're going to simulate, if we're going to build infrastructure that is for human users, like transport infrastructure and energy infrastructure, we need to include the various actors and stakeholders that come into play. And end users would be one, network operators would be others, regulators, those who provide policies, all need to come together in our design. So I will talk today about a state-of-the-art modeling approach, something that we are working on at Imperial College, which is called agent-based modeling, where we can simulate these different actors, these different stakeholders, the social as well as the technical components of our system. So yes, I want to use computers. The alternative really, if that's too difficult or too expensive, is to build it, see what happens, and after 15 years, maybe we have learned some lessons of whether this works. Obviously, when we are building our high-speed train links, when we are building our electric vehicle charging infrastructure, etc., we really just don't have that luxury. We want to plan our infrastructure in advance in a meaningful way. So today I want to go through a few case studies to use as examples and to explain how both the social and the technical elements there are important and how we include those in the decision support tools and in the simulation that we have, and talk to you on how that could influence business decision making. So I just use a few pictures to illustrate a range of application areas that I'm looking at, that colleagues of mine are working with in our research team. I'll start with the electric taxi. As you're probably aware, from next year, all new taxis with a registration to drive around London need to be capable of zero-emission driving, and that means that they need to have a capability to drive on an electric engine. So these are now coming on the market, pure EV range around 70 miles. They also have an internal combustion engine, they're hybrid vehicles, and 70 miles is not enough for a daily trip for a taxi driver. A typical shift of a taxi driver is probably around double that, 120, 150 miles in a day. So if they would keep using their vehicle as they are used to, they would still pollute central London with their internal combustion engine. They would still be driving on that. Whereas one of the main ideas behind this policy is to get our air cleaner and understand that if these vehicles drive on their electric engine, we don't have that emission in the street. If they run their internal combustion engine, we do. So what we are setting out here is to understand how taxi drivers operate their vehicle and how that then influences the need for charging infrastructure. And if we understand that, the technical capabilities as well as then the user, the person sitting in that vehicle that makes decisions on where to drive to, when to charge the vehicle, and then we can plan our infrastructure with that. Another example here in the agriculture sector, looking at the rollout of anaerobic digestion plants in the farming sector, where farms can process their waste using microorganisms that process the waste, the slurry of cows, the leftover of their crops, and generate a biogas from that, which you can burn to generate electricity or upgrade to pump into the grid. So this technology is old and well understood, but the uptake of that in the UK is very low. The UK government has ambitious plans for that, but only around 100 of those exist. The payback time is perhaps 8 years or 10 years, so it could be a good investment for farmers also to diversify their investment. But the the decisions of these farmers, they're in a different mindset as, my job is a farmer, I have my cows, I have my cereal crops, I'm not an energy producer. So the behavior of the farmers and the attitudes towards these new technologies changes that, even if it makes perfect business sense. So again, that's something we try to understand from that technical perspective. What are the flows of mass that would go into such a system? How much energy could we generate? How much emissions could we save to set up this bioenergy infrastructure in our country? But the behavior of the individual farmers make a big impact, and that needs to be well understood, and we need to experiment with different ways to address that. This bag of water is an example of a project we are running, sponsored by DFID, Department for International Development, on building water infrastructure in developing countries. In Ghana, a part of the population does not have access to safe drinking water, and they rely on buying bags like this for their drinking water needs. There we need to understand the demand for water and the waste that is being generated, human wastewater, and plan the water and sanitation infrastructure in that country, and to decide what are the right investments that we need to put, where do we put which technology, which pipelines do we need to build. So again, we need to understand the demand from a user perspective, and in these cases there's a lot of issues like cultural, religious, diets change, that all play a role in how people use water and the waste they generate. Then the final example, a bit closer to home here in London, the Queen Elizabeth Olympic Park, the former athletes village, were now turned into residential development. The buildings are all connected to a district heat network. So all the heating needs of these buildings come from a central plant and piped into this neighborhood, and the people don't have their own boiler. That the efficiency of that system is not as good as expected. It is not designed as well as it could have been, and the emissions from this are higher than expected. The efficiency is a lot lower. So we're trying to understand then what happens with the people in that building, the people who are operating their thermostat, who have demand for comfort in their home. What are those needs? So in all these examples, it's a technical system. Of course, you can look at your electric vehicles as a mobile battery, and as the cables that run in the ground, and charging infrastructure that we need to build, and all that is very important, and important to get that right. But I'm arguing that we also need to understand how people would be using that infrastructure, and the same with our farmers that are making these decisions, or the households that set the thermostat. So in my work and together with colleagues, we are building simulation models of all these systems. So I'll very briefly talk to you about how that works and what that looks like, and I've kept the same order as in the previous slide. So in the top left, looking at a simulation of taxis and electric vehicles driving around London, also in Isle of Dogs area near Canary Wharf, to understand the local demands in that area, and looking at the impact of the electricity on the electricity grid of the electric vehicle charging, as well as any other local demands that are happening in that area. Here we see a population of farmers, which we build in our simulation model of 175,000 individual farmers, with all the detailed characteristics of the kind of livestock they have, the amount of land they have, how much money they make, and also some of their attitudes towards renewable energy, attitudes towards farming, if that is a business for them or more of a way of life. And here we're simulating a population, or part of the population in Ghana, to understand the demand for drinking water in different parts of the city region. And we can do that at city region, we can do that at individual vehicle level, or we can zoom in on an individual building, where we are looking at the characteristics, the heat exchange between different flats in a block, understanding an individual's thermal comfort demand in one of these buildings, and how that is linked up, and how a collection of these is then running the demand for a large central system. So where do we go from here? So we have a lot of these tools that we are developing in a research setting, in testing different scenarios. These are flexible tools because we can grow them from the bottom up, because we have these synthetic populations. We can test different infrastructure implementations, different interventions, and different policies, and then simulate what the effect of that is. But what I would like to see, and what I expect to see, is that these kind of tools will become available on the desk of an engineer, of an architect, of a district D&O operator, so that they can test different scenarios in a flexible way on their computer and get real-time information on the possible impact of decisions that they make. And several companies are starting to build that, the software infrastructure for that. Consultancy companies are training their people for that, and companies like Arab or Bureau Happold are having teams that use this way of modeling to support the decision making in infrastructures. So that was my talk, and I'd be very happy to discuss that in the roundtable afterwards.
Thank you.